In this video, you will see how to tune a multivariable fixed structure controller using Control System Tuner. This Simulink model contains a block representing helicopter dynamics, as well as blocks representing helicopter flight control system. The control system consists of the blocks highlighted in orange, the 3 PI controller blocks in the outer loop, and the 3x5 decoupling matrix in the inner loop. So in total we need to tune 21 gains of this control system, which would be pretty difficult to do if we were using any traditional design methods. The control system must satisfy 4 requirements. The first requirement is to track set point changes in theta, phi, and r, pitch angle, roll angle, and yaw rate with 0 steady state error, 1 second response time, minimum overshoot, and minimum cross coupling. The second and third requirements are to provide strong multivariable gain and phase margins at plant input and plant output correspondingly. And the fourth and final requirement is to limit how fast closed-loop system dynamics is, not to excite flexible modes of the helicopter. The system is initialized with default gain values. PI gains are set to 1s, and the decoupling matrix is 0. If we run the simulation and look at the results, we will see that the system is unstable with this set of controller gains. So let's tune our control system. To do that, we will use Control System Tuner. We will go into Control Design menu and launch Control System Tuner. We do most of the work in the Tuning tab, where we go from left to right. So we start with selecting blocks to tune, decoupling matrix, and the 3 PI controllers. Next, we add tuning goals. First goal is desired step response. We want to have good step response tracking with minimal cross coupling between channels. The signals that are inputs are theta, phi, and r reference inputs. And correspondingly, the outputs are theta, phi, and r measurements. Next, we can specify what the response should look like. So in our case, we want first order response with a time constant of 1, and this number specifies how much the system can deviate from the first order response. So let's change this to 20. Now click OK to add this first goal. The next goal is multivariable stability margin at plant input. So this is that signal, and we want 5 dBs multivariable gain margin and 40 degrees multivariable phase margin. Similarly, we want stability margins at plant output. So that's that signal, and again we want 5 dBs and 40 degrees multivariable gain and phase margins. Finally, our last goal is to limit how fast the closed loop should be. To do that, we add constraint on closed loop system poles. We want their maximum natural frequency to be below 20 radians per second. As we add tuning goals, we get a plot for each tuning objective, showing us how close we are to meeting it. Here we can see that we are not meeting all of the goals with default gain values. Now we are ready to tune. We just press the Tune button, and the Control System Tuner tunes the 21 gains to try to satisfy all the goals we specified. Calculation is finished very quickly. The number here shows how close we came to meeting all the goals. The closer this number is to 1, the better we did in meeting all the goals. If you look through the plots, we see that we improved quite a bit in terms of how close we are to meeting these goals. The final step is updating block parameters with tuned values. If we go back to Simulink model, we will see block parameters have indeed been updated. If we run the simulation now, we see that we have fast, stable response with very good decoupling between channels. In this case, theta is commanded to step at time 0, phi is commanded to step at 3 seconds, and r is commanded to step at 6 seconds. As we see, changes in each of the 3 channels barely cause any effect on the other 2 channels, which is exactly what we wanted. This concludes the video.